In previous few sessions we've been talking about the importance of the eigenequation to quantum mechanics with the idea that to each observable, to each observable physical quantity that you can measure, there's a corresponding operator, quantum mechanical operator, that you use in the eigenequation. And the eigenvalues you get from that eigenequation correspond to the allowed quantized measurement values you get for that observable, that measurable quantity, right? And we wanted the eigenfunctions of that eigenequation to be orthonormal. And we also wanted the eigenvalues, which correspond to the allowed measurable values that you can get when you measure, we wanted them to be real. And you put those two conditions together, we then learned that the operator in your eigenequation has to be Hermitian. It has to satisfy a certain property. And I've written it out again. Here it is. Written in terms of the overlap integral, that notation. So if your operator A, your quantum mechanical operator, A hat, obeys this condition, for two functions, two general functions, then that operator A is said to be Hermitian. Okay? And then towards the end of the last session, we did half of the problem. We went the other way and said if you have an eigenequation where your operator, in general, let's say A hat, is Hermitian, so you start with that assumption that it is Hermitian, then you can prove the other way. It becomes like an if and only if type problem. You can prove two things: that the eigenvalues are real, and we proved that in the last session, and the other thing is that the eigenfunctions are orthogonal, and that's what we'll prove now. So we're tidying up the discussion of the previous session. So now let's actually prove that two different eigenfunctions of your eigenequation for an operator A hat, they're orthogonal. So now, but before I do that, notice, now I can rewrite, this is your, that's the condition for hermeticity, I guess is the word. Yeah, the fact that that this is Hermitian. It has to obey this equation. These two integrals have to be equal. Now you can rewrite this, these integrals in terms of brackets, in the Dirac notation, bracket notation. And in some ways it's sort of easier to remember what this condition is, the condition for the A hat to be Hermitian, because it's sort of easy, it's more compact. But have a look what's happening. So remember from the very definition of the bracket, Dirac's bracket, is that this gets written as this, right? So you'll have some function star, some other function, and your first function goes here, but without the star, and your second function goes here. Well, A hat operating on a function just gives you another function. So this whole thing's a function, so you can put it here in the ket part of your bracket. Okay? And similarly here, now this multiplied by this whole thing is just the same as reversing it. Like you can rewrite this as a bracket. Now here's the starred part, so we can put this in the bra and this unstarred, so put that in the ket. So when you write it in this form, it's more compact, and you can see effectively all that's happened is your A hat, your operator, has just moved to here. That's why I put this arrow here. So in a sense, if you move that arrow, well, it just goes here. Right? So if you think of the condition for an operator to be Hermitian, and you think of it in these terms, it's sort of easier. You just move the A. Okay, so That's a useful device to remember what the condition is for an operator to be Hermitian. Okay. All right. So at the end of the previous session, we proved that the eigenvalues are real. Okay. If this operator is Hermitian, and now we're about to prove that its eigenfunctions are orthogonal. So in other words, if you have two different eigenfunctions, the bracket, the overlap integral, will be 0. So that's what we're about to prove now. All right. So let psi m and psi n be two different eigenfunctions. Okay. And we're, as usual, we're working in a context where there is no degeneracy, right? So for each eigenvalue, there's only one eigenfunction, right? So let's assume then that these two corresponding eigenvalues are different, and therefore these two eigenfunctions also different. Okay, and that's assumed here. So we're talking about two different eigenfunctions, and the two eigenvalues have different values. That's the assumption, and we're trying to prove then that the bracket of psi m and psi n will be 0. In other words, they are orthogonal. That's what we're trying to prove. All right. So put that as a bra here and ket it. That's a verb. With psi n. Okay. So do that on both sides with this and this. So that will give you here, with this in the bra part. So it'll give you lambda m psi m, and you've got psi n here. Okay, so this bracket equals this bracket. Now, this eigenvalue here. Now it's on the left-hand side, right? So if you translate back from the bracket to the eigenvalue, it gets starred, right? So if you've got a constant here, it'll also get starred. Whatever's here on the left in the bra part gets starred. You conjugated. The i's become minus i's. We'll see an example fairly soon. So if you take this out, this constant, it's just an eigenvalue. It's just a scalar, right? So if you take it outside, it'll get starred. It'll be conjugated, and that comes from the very definition of the bracket. Right? Whatever's here is starred in the integral notation. Okay, so this comes out, gets starred. Right? So then we're just left with the bracket of psi m psi n. But we've already proved, we've just proved at the end of the previous session that the eigenvalues are real. Okay, so the conjugate of a real number is just the real number. So you can rewrite lambda m star just as lambda m. Okay, so we've now got that. Now I've drawn an arrow here. We can rewrite this as we can bring the a. Well, see, if we go this way, we can take it back again, right? So we can take this back to here. That's the definition of a hat being Hermitian, right? So we can have it here, or we can have it here, right? So I can move this a from the bra. I can put it here as in the ket, okay? And that's what I've done here. So I can rewrite this as this. Why? Because a hat is Hermitian. I can do that, right? But then, what is a hat psi n? Well, it's lambda n psi n. Okay. Now this is on the right. This is in the ket part. It's on the right-hand side. So this constant here we can bring outside, and it doesn't get starred. It just stays as psi lambda n. So we get this here. Okay. So now we've got lambda n bracket of psi m psi n. Okay. Now all those terms were equal. You know, this equals this equals this equals this equals this equals this, which equals this, right? So in other words, this one and this one, since they're all 1, 2, 3, 4, 7 terms, they're all equal, right? So this one and this one here are equal, right? Which is what I've written down here. So lambda m bracket psi m psi n is equal to lambda n